You may have guessed I'm a theoretical physicist rather than an experimental physicist, and so I'd like to begin in the spirit of openness that Lisa started with this morning. Hello, my name is Patrick. I'm a recovering theoretical physicist. When I was a graduate student, I too tried to quantize gravity. It started with just dabbling with field theories on curved space-time backgrounds around black holes, but by the end, I kind of lost control and I was reading about string theory and stuff. Fortunately, after my PhD, I had to get a job, and LIGO was hiring. So that's when I converted to gravitational waves. And now you'll see what the aftermath 20 years later. So I work at Cardiff University. It's a nice school in lovely Wales in the United Kingdom. I've been there for the last 15 years, and it's been about 20 years since I joined the LIGO collaboration back in 2001. My work for LIGO, as part of the collaboration, has specialized on the detection of gravitational wave transients, but not binary signals. So I do data analysis, I look for gravitational wave signals, but not the ones we find, the ones we can't find so far. Things like supernova or accretion disk instabilities or perturbed neutron stars, those sorts of things that sort of go boom, but for which we don't have accurate models. And so particularly I focused on looking for those sorts of signals that are associated with things that we see externally, such as gamma ray bursts or supernovae or other messengers. So what I'd like to do today with my lecture, I've been asked to talk about the physics of LIGO and Virgo. And so I'm interpreting that fairly broadly. Eric Katsavanides, the next lecture, is going to talk about the detailed results that have come out of these experiments. I'm going to start with this talk with just trying to lay out the basic ideas, the physics of how LIGO, Virgo work and detect things, and sort of rules of thumb to understand in a hopefully not too technical way how we actually can detect things with these instruments. So I'm going to start with this cartoon, which explains my philosophy. Okay, so I find it funnier than that, but that's fine. So the idea, this is obviously the science is very technical. When you read the literature, of course, the literature is almost by definition technical, right? Scientific papers on gravitational wave detection and sources, etc. And so I'm going to try to focus where possible on rules of thumbs and analogies and so on that will give you the understanding of how things work. And then I have references to the literature. You can read the papers if you want all the nitty-gritty details. All right, so this is the outline. I'm going to start with this lecture. Basic principles behind gravitational wave astronomy. So I'm going to talk briefly about gravitational wave emission and the quadrupole approximation, main source types, and the basic idea behind how we detect each. Most of the talk will be spent actually on the topic of detector networks. This is one that doesn't get quite as much attention as I think it deserves anyway. A lot of the science talks regarding LIGO and Virgo focus on the idea of matched filtering for binaries, and they really focus on what an individual detector can do. As we'll see, networks of detectors are actually critical for getting science out of these observations, for getting most of the science out. Eric is going to talk about the science results starting this afternoon and continuing tomorrow morning. And then on the end, on Friday, I'll wrap up with talking about future results that we expect from LIGO, Virgo, Kagra, LIGO India, and from the Einstein telescope and Cosmic Explorer. All right, so quick introduction to gravitational waves and linearized gravity. So Alessandra did a really nice summary of this yesterday in her lecture, so I'll be brief. I'll just note that if you want to go into the details, I strongly recommend the textbook by Hartle. It's a really good book. It's the one I use with my undergraduates because Hartle, in his approach, he emphasizes the physics behind what's going on and then introduces the mathematics as needed to model the physics, rather than starting with 100 pages of tensor calculus and then trying to tell you what it all means. So I strongly recommend that. This is an excellent tutorial by Anna Flanagan and Scott Hughes. Just search for Flanagan and Hughes 2005. It's a tutorial on the basics of gravitational wave physics, gravitational waves. If you don't like the sort of standard approach to transverse traceless gauge, etc., they have an alternate approach where they look at they decompose the metric perturbation for the gravitational wave into components, and they demonstrate in a very nice way that there are only two components that solve a wave equation. It's a really nice alternate view to linearized gravity. All right, so let's look at the key equation number one. So we'll take a flat space-time background, we put a perturbation on it, as we all know, and as Alessandra showed yesterday. The perturbation in appropriate gauge obeys a wave equation, right? So we've got the wave operator on the left. You'll note 1 over c squared, which means that the waves travel at the speed of light. And then you've got a source term on the right-hand side. So this is what we call the stress tensor. It basically just describes the distribution of mass and energy in your space. So it's the source of the waves, of the perturbation. And then the thing that normally gets ignored is this coupling constant. And it's normally ignored because we usually use units in which g and c are equal to 1, yeah? Natural units. But if you actually work them out in SI units, you get probably one of the smallest numbers you'll see in physics, right? 10 to the minus 42 in standard units. And what that means physically is that you have to put a literally astronomically large amount of mass and energy into the source to get any kind of detectable wave. Because whatever your source is, it gets suppressed by 10 to the minus 42 before it gets turned into a wave. So roughly speaking, that's why gravitational waves are really, really hard to see, hard to detect. Because they're very hard to generate at any reasonable amplitude. If you work through the details, of course, we come up with, you're able to show that this perturbation contains only two radiative polarization states. We all know the plus and the cross. And they do these classic quadrupolar deformations in the geometry, right? So if the wave is traveling in this direction, they do this sort of stretching and squeezing pattern, or 45 degrees, right? So if we go on from there, let's look at the generation of these waves. Okay, so this is the quadrupole approximation. I've written it in probably the simplest form. So you've got the wave solution due to a source. So this mu is the mass density. It's what in Newtonian physics would be the distribution of mass per unit volume as a function of position. This r here is the distance to the source. So the wave we measure at time t depends on the mass distribution at time t minus r, of course, the so-called retarded time. So you take the mass, you multiply it by 2 powers of position, integrate over the source, 2 time derivatives. So this thing is basically your quadrupole moment. You take 2 time derivatives, and you multiply by, again, this 10 to the minus 42 number, and you get your wave. So this is, of course, this is the lowest order approximation for the gravitational wave emission. This is not enough if you want to do accurate modeling of binary in spirals and source parameter estimation, etc. But what it is sufficient for is estimating what we can and can't detect. So if you just take 2 point masses representing your black holes, put them in a Keplerian orbit at some distance, and you just evaluate this, you'll get approximately the amplitude of the signal at the Earth, and that will tell you whether or not those black holes are close enough to detect or not compared to your noise curve. So it's sufficient for that. If we want the full details, of course, Alessandra went through this very nicely yesterday. The post-Newtonian expansion goes beyond the limit of slowly moving sources, and numerical relativity in particular, and post-Minkowski go beyond the weak field approximations. So you need those for the accurate parameter estimation, but for basic arguments about what we can and can't detect, you can just stick with the quadrupole approximation. So I wanted to note 1 or 2 things about it. It's not obvious from looking at it. We call it the quadrupole approximation because it involves a quadrupole moment. If you decompose the mass, if we go back, if I decompose the source, the mass distribution, into spherical harmonics, I can work out how much gravitational waves comes out of each of the spherical harmonics. And it turns out, again, because it's a quadrupole approximation, right? So these are the L equals 0 harmonics, the L equals 1, the L equals 2, L equals 3. The quadrupole approximation gives you exactly 0 for everything except for the L equals M equals 2 emission, right? It's quadrupole. So again, it's just another a limitation of the quadrupole approximation that it only measures this L equals M equals 2, the spherical harmonic moment. The other modes are exactly 0 in this approximation. However, higher mode emission from these sorts of perturbations, it does exist in the full general relativity, but actually it's only detectable in a very small fraction of sources that we know of so far. So again, the quadrupole approximation is actually good for at that level for just about everything we've detected. So here's a specific example. This is an image that shows all of the gravitational wave detections by LIGO Virgo to date. They're mostly binary black holes, so each one of these boxes represents 2 black holes merging into a larger black hole, or in some cases neutron stars. These 2 are the only 2 for which we have statistically significant evidence of being able to measure L greater than 2 radiation, the higher modes. For the other 88 or 89 systems, we can't measure anything other than L equals M equals 2. So the quadrupole approximation is surprisingly good. Those higher modes will be important in the future because in principle they allow us to break the so-called inclination distance degeneracy. So this is an image from the very first detection, 1509-14. This is the distance versus inclination plot. So this is from the full Bayesian analysis of the data. This two-dimensional, on the x-axis, it's the inclination of the orbital axis of the system to our line of sight, and the vertical distance is how far away the system is. Now, binaries like to emit preferentially along their orbital angular momentum axis, along the orbital axis. So the possibilities are, if you see a given strength of signal, it could be that it's a binary that's very far away from you but pointing its strongest emission right at you, sort of face on. Or it could be a binary that's closer to you but edge on, and you're only getting weak emission. And it's hard to tell the difference between those two. And that's why what you see this degeneracy here. It looks, for this particular signal, there's roughly 75% probability that it's sort of face away, maybe 25% probability it's face on, some small probability it's edge on. But we can't really tell for certain. And that's because the two gravitational wave polarizations, the plus and the two spherical harmonic moments, the m equals 2 and minus 2, basically the plus and cross polarizations give you almost the same emission strength as a function of inclination, but the higher L modes don't. So in the future, if we can measure these higher modes, we should be able to break these degeneracies and do much better constraints on things like the Hubble constant. So this is an image from the Hubble constant paper associated with the binary neutron star detection 1708-17. So you may be familiar with this. I'm sorry, the axes are, I can see they're a bit blurred. The horizontal axis is the Hubble constant that was inferred from that measurement. So the idea there was, again, we had a gravitational wave detection from the binary, and we had correspondingly a known host galaxy from the electromagnetic counterpart that was observed. So we can measure the distance from the gravitational wave emission, we can measure the redshift from the counterpart, or the counterpart's galaxy, and between those you can work at the Hubble constant. The problem is that we don't actually know the distance that accurately. So if I go back one slide, this is for a different system, black holes, but it's generic for rotating systems. We have this degeneracy. It's hard to tell the angle at which you're viewing it versus the distance. And so there's a large uncertainty generically in the distance based on not knowing the inclination. So this vertical axis shows the inclination. These are the contours of containing 90% probability. You can see that actually there's quite a large uncertainty in the inclination, which corresponds to quite a large uncertainty in the distance, which means then quite a large uncertainty in the Hubble constant. So those higher modes will be important if we can break these down. If we knew, for example, a specific inclination, if we knew the inclination was, say, minus 0.9 in cosine, then you'd have a much more restricted range of Hubble constant values. Okay, so one last thing, probably all aware, but it's worth remembering, that even in full GR, the spherically symmetric mode gives you zero gravitational wave emission, and that's a shame. It's called the Birkhoff theorem. It's a shame because a lot of compact objects tend to be round, right, because of their strong self-gravity. So, for example, core-collapsed supernovae, they're not perfectly spherical, but they're, fairly spherical, and it means that the amount of emission you would get from, say, a collapsing star is not as large as you would expect given the total mass involved. It's only the mass that's sort of moving in a non-spherical way that gives you gravitational wave emission. Okay, so let's just take this just a step farther. What kind of sources can we detect given the quadrupole approximation and given a detector spectrum? So this plot is from what we call the Observing Scenarios paper, 1304-0670. It's a great reference if you want to know what LIGO and Virgo and Cagra have been doing historically and what our current projections are for the future. And Lisa showed plots from this, projections for our upcoming observing runs, etc. So I just pulled this example. This shows the noise spectrum for the various LIGO detectors over the science runs to date and projected into the future. The key thing is the frequency band. All right, as Lisa explained, we can't see down below about 10 or 20 or 30 hertz just because of the seismic noise and control noise. So really we're limited in observations to something like 20 or 30 hertz up to a few thousand hertz. So you combine that with the quadrupole approximation. So for a rotating quadrupole, again, you've got the mass and the r squared. That just comes from the definition of the quadrupole, and then the omega squared factor comes from your two time derivatives, right? So the thing is rotating or revolving some manner, and then 1 over r distance. So that gives you an order of magnitude of the gravitational wave strength. If the thing is in some, like a binary in a Keplerian orbit, you can apply Kepler's law, simplify it further. So we've just got the square of the mass, the size of the system, and the distance of the system. And then this epsilon is some number that captures how non-spherical, how much of your mass is in the quadrupole versus spherically symmetric configuration. So if you combine, so I take this take this approximation, and then I can look at, again, the frequency range over which I can measure things. Well, if I can only measure over a certain band, say 30 to 3,000 hertz, the object has to be moving coherently to generate gravitational wave emission. That means it has to be smaller than a certain size. So just sort of speed of light arguments tell you that the size of your object can't be bigger than speed of light over the frequency at which you're measuring. And that gives you a range of sort of 100 kilometers to 10,000 kilometers as a characteristic size of object that you could see with this, in this bandwidth, in this range of frequencies. It's not precise, but it gives you an idea. So what that really means, 100 kilometers, solar mass, it means you're talking about something that's a black hole or a neutron star. A white dwarf star, okay, a white dwarf has a radius of around 7,000 kilometers, so that's about, about at the upper limit. But if you put two white dwarfs in a binary, then of course they're more than 7,000 kilometers apart. So this really limits us to, what you can do with this frequency range is look at objects of this size, basically. That's more or less how it works. So small and dark is what we're left with. We're looking for high mass, small radius objects, means very high density objects. So another result of this is because you see very high density regions of space or space-time, it really means you're looking into the cores of systems. So for example, in a supernova, you've got a supermassive star that's blowing up. It's really only the inner couple hundred kilometers of the core where the density is going to be high enough that you can see gravitational waves in a frequency band. So you're really looking into the cores of objects. That's actually really cool now when you combine it with a core collapse supernova observations, for example, where we see the light from the surface, gravitational waves and neutrinos from the core. They're complementary messengers. So it'd be very exciting, but it's just something to keep in mind. So our prime sources are things like neutron stars and black holes. As I mentioned, white dwarf binary is a bit out of band. If we go back to this approximation here, so for a binary system, you just fill in some numbers, right? Square of the mass, size, and distance. If I take the closest gravitational wave to date, the binary neutron star event at 40 megaparsecs, you get an H that's around 10 to the minus 22. So, we all know this number. It's ridiculously small. But that tells you then the experimental challenge that you face. So the spectrum, right, this range tells you what size of objects we can see. And then that calculation there, that 10 to the minus 22, tells you how far down this bottom of your bucket has to be to have a hope of seeing anything. Okay, so in the end, we see what we're looking at with the current generation of instruments are the corpses of dead stars. So we've all seen this, people. I figure the bar for humor in a physics talk is not very high, so I figure I can get away with this sort of thing. Right, now Eric is going to talk about gravitational wave sources and what we've seen, detection methods, what we've seen in this afternoon's talk. So I don't want to take too long here, but I just have to highlight the basic classes of what we look for so that we can then understand when looking at a network of detectors what a network can do and what it can't do. So I'll be fairly brief here. Of course, we're all familiar with compact binaries, right? In-spiral merger and a ring down of a pair of black holes or neutron stars. The signals are modeled accurately by post-Newtonian theory and numerical relativity, as Alexandra showed us. This is an example, right? The first gravitational wave detection, 150914. If you look at the axis, this is a fraction of a second. If you go to lower mass systems like binary neutron stars, they last longer in the LIGO frequency band, so they can last up to tens of seconds or at a stretch maybe up to 100 seconds. And so what that means in practice, when you do your matched filtering operation, you're operating on fairly short stretches of data. So I think a typical FFT length used by some of the search codes is 256 seconds as an example. So a fairly short chunk of data, you can do a sensible analysis of that. In this case, if you look at again, this is the noisy data you see here. That's the bandpass data from LIGO Hanford, and then you can see this thin yellow, sort of smooth yellow trace. That's the best fit gravitational waveform from models. And of course, the main idea with matched filtering, right, is you have a bank of such models that cover all possible mass and spin pairs, spin combinations, and you just filter them over the data. And when you get one that is a high match like that, that tells you you've likely got a signal there. That's the basic idea. And again, you can do this with fairly short stretches of data. Now, I hope you'll forgive me. I'm going to indulge just one quickly thing. This is a couple of slides that I use in all of my public lectures, so non-technical, general public. So I don't mean to be patronizing. I just think when we do this science, it's amazing. Like the numbers that Lisa was showing us this morning for the sensitivities of these instruments, the things we can measure, I find them completely boggling, especially as a theorist, right? I can't imagine coming up with this stuff. So I just want to take a minute or so to show you what I show the general public that really boggles me every time. So the strongest gravitational waves we've measured, right, like 150914, the peak strain is about 10 to the minus 21, which means they stretch, right? The arms get stretched or shrunk by 1 part in 10 to the 21. So what does that actually mean? Well, this is the Hanford Observatory, right? That arm length is 4 kilometers. So let's go in from 4 kilometers. We can all do the math. 4 kilometers times 10 to the minus 21 is a really small number. But if you walk through it in steps, I just find it impressive. So I hope you'll indulge me for just a moment. So here's the detector. What I want to do is go in steps of several orders of magnitude at a time. So I'm going to zoom in a factor of 10,000. 4 kilometers divided by 10,000 is about a foot, right? Which is about the size of the mirrors, right? Length or diameter of the mirrors, order of magnitude, right, in the detectors. So if we zoom in by 10,000, you're talking something about that big in effect, right? Much larger than the gravitational wave. So we have to go in a lot further. This is a scanning electron micrograph image of a silicate, some silicate material. So you can just barely make these fuzzy white dots. Those are the individual atoms, right? And in the lower half, the authors have very helpfully colored the atoms. Apparently silicon is greenish and oxygen is red in this plot, but you can see the individual atoms. This is about the smallest thing we can directly image, right? So that's a factor of 100 million, 8 orders of magnitude smaller than the mirror, right? Count them up, that's 12 orders of magnitude. We're only about halfway there, right? And we're down to the smallest things that we can image. So we're gonna invoke the authority of the Big Bang Theory show. Everybody, you've all watched it, right? Yeah? Okay, yeah. So we all know from the Big Bang Theory that that's what atoms look like. So I'm gonna pull out one of the oxygen atoms, that's it, yeah? So that's a factor of about 100 roughly from that image to one atom, sure. Okay, but this is a lie because we all know the nucleus is actually about 10 to 100,000 times smaller than the orbital size of the electron orbitals, right? So really the nucleus looks more like that. So that's a more realistic atom. Electrons are not to scale, obviously. So let's zoom into that nucleus. So I'm going to jump in a factor of 10,000. I've now got my nucleus. I have it on good authority from Barry that the protons are orange and the neutrons are kind of that greenish blue. We're still not there. Let's go in another factor of 10. I'm going to pull one of the protons out. Yeah? So we're down to the proton scale. Now, you can count up the powers here. It's 10 to the 19. We're still a factor of 100 away. And we're looking at this, a length change in the arm of the size of a single proton, right? So to get to 10 to the minus 21, I can't do it properly on this slide because I don't have the resolution. I've tried to make that gap 1/100th of the proton size, but it's not quite small enough. So that's how far down we have to measure length changes, relative length changes, to measure the strongest parts of the strongest signals. I find it, absolutely amazing. So my hat's off to the people who are able to who conceived and constructed these instruments and continue to develop them to even higher sensitivity. Okay, just one last wow thing, very quickly. Again, just with the first detection, because that was the most dramatic one, I guess, for most of us. You can work out the luminosity. Alessandra showed you get this factor of G over C to the fifth, right, in the luminosity. And so that's basically just a universal constant. So any black hole merger signal at its peak will be emitting roughly G over C to the fifth energy. It works out with a factor for mass. So for this particular first detection, 3.6 times 10 to the 56 ergs per second. And you can look it up, and you add up all the light from all the stars in the universe, that's 10 to the 55 ergs per second. So for a tenth of a second or so, this one system emitted more power than all the stars in the entire observable universe, right? But it was completely black. If you're on the outer edge of that solar system or wherever it happened, and you were looking right at the event, you would have seen nothing. There's no light, there's no particles, there's no debris, there's just these vibrations of space-time, which you wouldn't have seen unless you had a pretty sensitive instrument. Right? Strains still would have been something like 10 to the minus 11 or 10 to the minus 12 at 100 AU. So you wouldn't know. This was, at the time, I would call it the most powerful explosive event humanity had ever seen, right, since the Big Bang. And we've seen more powerful ones since. So it really is amazing what we can do with gravitational wave astronomy. Okay, back to the science. I'm going to quickly cover the other sources, just one slide each, to motivate. So that's CBCs. That's everything we've seen so far. Let's talk about the other sources briefly. So we've got continuous waves. The main idea here is pulsars. So you've got a neutron star. It's spinning on it's spinning, but it's got typically, for pulsars that we observe electromagnetically, it's got a magnetic field. The magnetic axis is not aligned with the rotation axis, and so as it spins around, if the magnetic axis sweeps across our line of sight, we see a beam of radiation and pulses, right? Hence a pulsar. If this star is not axisymmetric, if it has a quadrupole moment, then because it's spinning, it's going to be emitting gravitational radiation. And the quadrupole formula tells you, to high accuracy what that's going to look like. It's basically just going to be a sine wave. A steady sine wave that may be very slowly decreasing in frequency as the star very slowly spins down. But basically, you're filtering the data looking for a sine wave. And the complexity comes because, of course, the Earth is moving, and the pulsar, the Earth is moving, which means the pulsar relative to us is moving on the sky. So that sine wave may be modulated slowly in frequency over the course of the day and over the year. So you have to filter for those effects, but in the end, it's basically just a matched filter search for a sine wave that's been modulated. So the signal is continuous. It's on all the time, at least on time scale of years, long compared to our detectors. So ideally, if you want a matched filter, you would filter on your entire data set, say of order a year of data or multiple years. In practice, that's difficult to do for anything except for known pulsar systems. So often searches, sort of blind searches for pulsars, use shorter FFT lengths. They're suboptimal, but practical. Okay. Bursts. So this is my area. I'll be very brief on it. The idea is that we're looking for anything that goes boom, gives us a brief transient signal that's not a compact binary. If those are well modeled, we use match filtering. We're looking for anything else for which we don't have an accurate model. Examples would be core collapse supernova. The simulations are still not robust in terms of predicting gravitational wave emission. Other possible sources include speculation about, for example, instabilities that might develop in accretion disks around, say, a black hole and accretion disk from a binary neutron star merger. You could have transients. This is an artist's impression of a flare, a giant flare from a soft gamma repeater, for example. It might cause the crust to vibrate and then emit radiation at various frequencies. The basic idea here is to use what we call excess power techniques. It's an old technique. It's more than 20 years old. But basically, you scan your data stream, and you just look for a jump in the power in some time frequency region, a hotspot effectively on the map. And we'll see lots of examples of those. That's fairly basic, somewhat crude. You then require that you see that excess power in two or more detectors and that there's some correlation in the data between them. Again, going back to this idea of a maximum size of sort of 100 to 10,000 kilometers and a frequency band of sort of 30 hertz to 3,000 hertz, it means that effectively we wouldn't expect this. It's most likely to have signals on sort of the millisecond scale, perhaps up to a few seconds. That's where most of the effort focuses. There's some effort to go beyond, to tens of seconds, hundreds of seconds, thousands of seconds, but most of the searches concentrate on that region. And so you can cross-correlate on fairly short time stretches to find your signals. Right. And then the last of the classic four source groups are the stochastic gravitational wave background. So this would be the case if you had either a superposition of many unresolved sources, such as all the black hole and neutron star binaries out there in the universe that are a bit too far away for us to resolve, but that would generate sort of a background hiss. It's also possible we could have an early universe, a cosmological background from the early universe. That's not likely to be detectable unless something interesting happened, like some sort of strange phase transition, etc. But nevertheless, it's a well-defined type of source, and it's a well-defined way to search for them. You take two detectors, and you don't know what the signal in each detector is going to be because it's random. It's a random superposition, but you know they should see effectively the same signal, up to the fact that they're separated by some distance. So there'll be some delay between them. And so basically, you cross-correlate pairs of detectors. And again, because of the frequencies we're looking at, the individual cross-correlations can in principle be evaluated on short time scales. You need to integrate over a long amount of data to build a signal-to-noise ratio. But you can do the operation with small amounts of data at a time and build it up. Okay, so what I wanted to focus on here was what you can do with gravitational wave detector networks. Right? So we've got the basic ideas from the quadrupole approximation, the type of sources we can see, the basic classifications, and the basic idea of how we search for each. So I'll just remind you something that I think we've all seen, but it's good to keep in mind. I'm just going to take a guess here. How many people here have done an actual course, university course on gravitational wave astronomy, or gravitational waves? Yeah, I'm getting like about a dozen. And how many people have done some kind of course on astronomy, like with telescopes? And yeah, just about everybody, right? So just about all of us have much more background here than in here. So it's worth just pointing out, again, these differences, these comparisons. So electromagnetic waves, of course, we accelerate charges, electrons, for example, whereas we know we get gravitational waves basically from quadrupole moments, accelerating quadrupole moments. What this means is that for the gravitational wave, it has to be, because you're looking at the entire source as a bulk, it has to be coherent bulk motion to give you something reasonably strong. Whereas, of course, electromagnetically, the surface of the sun, each atom on the surface can be emitting separately. And that means that for the sun or some other object, the wavelength that you're getting out is much smaller than the bulk of the source. You can image the sun or a planet or something. With the gravitational waves, because it's the entire body that emits, that means that your atom, right, is the entire binary system, for example. You can't actually resolve. So we can't resolve with these. It's much more like listening than looking. Right? electromagnetic waves have these issues about being, well, they interact readily with matter, right, because it's charged, whereas gravitational waves don't. They'll pass through anything, right? We routinely detect gravitational waves coming from below us through the Earth, right, because the Earth is transparent to a gravitational wave. And then as we've seen, that the frequencies are much, much lower, the characteristic frequencies that we deal with than, say, in astronomy, where you're looking at typically megahertz, gigahertz, and much higher. So if you put these two together, compared to an EM observatory, gravitational wave detectors are, as we'll see, basically all sky monitors, and they're very low bandwidth because of this low frequency, low data rate. And so that means that it's easy to observe basically all the sky most of the time and save all the data. It's easy to do archival analysis. If somebody says, well, since somebody noticed something last week, can you look in your gravitational wave data? Yeah, that's easy. We've got the data from last week and from last year and from the last decade. As we'll see, source localization is very hard. If we see something in the data and we want to tell an astronomer, oh, we just saw something, can you point your telescope? It's a real challenge to tell them where to point. Okay, so we'll go into that. Okay, we've all seen this, the basic idea of a gravitational wave detector, right? Laser interferometer looking for these tidal deformations. Okay, a little more detail. This is what we call the antenna response function. So the way that when the gravitational wave comes in, if it's coming from, as we know, if I have my two arms, X and Y, the laser, if the gravitational wave is coming from directly above or below and has the right orientation of its polarization, it'll stretch and squeeze those two arms, right, maximally. And you get a strong signal. If it's coming in, say, from the direction along one of the arms, because it's a transverse wave, it's not going to stretch this arm, only that arm gets stretched. So you get a weaker signal. And if it comes in from the 45-degree bisector of the two arms, it's a common effect on both arms. You get zero signal at all. So this is what we call the antenna response, the way that this sensitivity depends on the orientation of the gravitational wave coming into the detector. So this image is a sky map. It's not a very feature-rich map, but this is actually really fundamentally important because this is how all interferometers work, how they all see the sky. So this particular example is for LIGO Livingston. It's a mole-wide projection. So you've got sort of the North Pole, celestial North Pole, South Pole, and then right ascension across. So what you see is this bright yellow spots. This is where you're at maximum response. We'll call it 1. The precise formulas for the response to the two polarizations are given here in terms of the angles to the arm and the polarization orientation of the signal. This is a good reference. It's a good reference because in the appendix of this paper, they list the actual locations and orientations of most of the main detectors. So if you go there, you can figure out what the actual real angles are for a given point on the sky. That's why I include that one. So this is, again, specifically for the Livingston instrument. You've got one bright spot here, one bright spot there. So that's directly overhead the Livingston detector. And that is the opposite side of the Earth, the antipodal point from the Livingston detector. So it's really good at seeing directly above or directly through the Earth. And then these 4 black spots, 1, 2, 3, 4, that is sort of this one. Those are those points that are bisecting 45 degrees to the arms. Those are what we call the nulls. They're the only spots on the sky where you have exactly zero response. If you aim the gravitational wave right down those lines, you see nothing. The detector sees nothing. And so it's important to have multiple detectors. We'll come to that in a moment. This may not look, I'm not sure how impressive this looks because, with the color scale, but you can do the numbers. So if I say the peak value is 1, the minimum is 0, find the point where it's, which is at 0.5, roughly the edge of the green. If you calculate it, your mean square antenna response is greater than half over about 65% of the sky. So this is why we say they're all sky monitors. One detector sees, well, depending on how you put the threshold, it sees about 2/3 of the sky with at least half its maximum response, right? Which is really, really good. So a couple of these things can easily cover the entire sky. The downside is, because of this very weak response, you can see that these patterns varies very slowly over the sky, right? I can go many degrees off of peak or around here without a big change in the antenna response. That means it's very hard to tell where the signal came from once you've detected it. So this is an example. Again, this is an event 1904-25. This is the second binary neutron star merger detection. And this was detected, so here's the reference. The LIGO Livingston detector and the Virgo detector were operating at the time, but the Virgo detector saw very little signal from this. It was effectively only seen by Livingston. So this is as close as I could find to an example of seeing an event with a single detector. And these contours are the containment, the probability maps. Right, so the outer containment contour is the area that contains 90% probability of the signal. It's just shy of 10,000 degrees, which is 1/4 of the sky. Right? So the map-make structure, I wasn't quite able to get the alignment perfect, but basically what's going on, Livingston sees really well in this direction and really well in that direction. It doesn't see very far in these directions. So if you have no other information and you do a Bayesian analysis, the Bayesian analysis falls back on its priors. And the prior is, if I'm looking in this direction, I can see 2 or 3 or 5 times further than if I'm looking in this direction. So 5 times further is 125 times more volume, much more likely to have come from here or from here than from one of these directions where I can only see a very small volume of space. And so the reconstruction basically gives you a blob over Livingston and a blob on the antipodal point underneath Livingston. That's your best guess for where the gravitational wave signal came from. And again, it's only localized to about 1/4 of the sky. So if you tell your astronomer friend, I just saw a binary neutron star merger, they say, great, where is it? I'm going to point a telescope, and you give them this. It's not ideal. So we really need to have multiple detectors. This is really, really important. And we have several detectors obviously operating right now, but for the next generation, we're going to be hearing talks about Cosmic Explorer and Einstein Telescope. Those are, of course, separate projects because they're on separate continents and separate funding agencies, but it will be really important for the future to have more than one of those projects go ahead. They both have to go ahead, or there have to be detectors at multiple sites in the next generation, or we're going to wind up with a lot of these, and that would be a real shame. Okay. So another issue with doing single detector observations, if you only have one detector operating, is that you're vulnerable to noise. Effectively, there's very little you can actually detect. So that binary neutron star merger I showed is sort of a rare example of something you can do with a single detector. So this is the truth. The actual data from LIGO, Virgo, Kagra, they contain non-Gaussian noise transients. We call them glitches. And they are very, very common, as we'll see in a minute. There's a very nice paper. It's called the Gravity Spy Project. They do classification of glitches in the LIGO data. They've come up with about 22 or 23 classes to date of individual glitches. I just pulled out a couple of them, for example. So these images show the power as a function of time versus frequency for 4 of the known types. This is an air compressor glitch. This is a nasty one. This is the blip glitch. This is the most common of all the glitches, and it is the bane of burst searches because it's a featureless pulse that looks like any other featureless pulse that nature might contribute to us, might give us. And this is one where we don't know the source of it, and we'd really like to get rid of it. So-called helix glitch, and this one is quite cute. This is the koi fish. It's so named because it looks kind of like a koi fish swimming around a pool. So similar in structure, a little more complicated than blips, but also quite irritating. So the data is full of these. This is an example. This plot is from the latest so-called catalog paper that LIGO and Virgo and Kagra produced. So here's the reference. This shows the rate of glitches in one of the detectors, the Hanford detector, basically over the first half of that O3 run, the so-called O3A run. And what you can see, I mean, there's several different traces, but basically if you just follow the red trace, sort of a median day by day, this is the rate of glitches per minute where the signal-to-noise ratio of the glitch is at least 6.5. So that's loud enough that you can just look at one of these time frequency maps and you can see it. And if you're running a search code on the data, the search code is definitely going to see it. And what you see is typical rates of order 1 per minute, sometimes much higher, 10 per minute. There was some improvements to the detector, the Hanford detector done at this point that eliminated one of the classes of glitches and the rate fell down. But still, it's 1 every 2 minutes or so typically. So these glitches are really, really common. And this is a disaster if you only have one detector, because what happens? Well, I do my search. So these are the sorts of signals we have seen before and we expect to see again. And these are the competing blips that are showing up in the data. Yeah? So we've just seen these 4 glitches. Suppose I'm doing a search. I've only got one data stream. I filter my data. We're looking for compact binary mergers, black holes and neutron stars. And one of my templates matches something in the data. Well, if it's a blip, if the thing is in a blip doesn't look much like an in-spiral, but it looks a bit. If you do a match filter, the dot product of your match filter template with any one of these waveforms, you'll get some non-zero result because there's excess power in the data in each of these cases. So your search code will ring off and say, I found something with an SNR of X. And based on this plot, you expect your search code to be ringing off at least once a minute, right, of order. And so if you analyze the data from a single detector, you're looking for these signals, but you get flooded by these. And of course, you can't send out alerts saying every minute, we might have seen something, we might have seen something, when these events come in sort of once per few days, and this once per few months, and this is once per minute. So what you can do with a single detector is do a detailed comparison of the waveforms, here and here, to these morphologies. So for the binary neutron star, I hope it's visible here. The axis here, that's minus 10 seconds from merger up to 0. So this is 10 seconds of signal, and in fact it was visible earlier in the trace as well. What you can see is that, of course, this is a very long-lasting signal that has a very precise frequency change over time. Yeah? It doesn't look like these four shapes. These shapes are all, each of these plots is about half a second in duration. Yeah? So if it's this template that rings off, right, you can compare this duration to the duration of the event in the data, right? So you're not going to confuse a blip glitch that's a tenth of a second long with a 10-second long binary neutron star signal. That's fine. When you run the binary neutron star template over your data and the blip occurs, it rings off the template, but basically you can do a chi-squared test. And it does ring off the template, but the shape of this template doesn't match the shape of that signal, so you can throw away the event. That's great. But these are rare events. We've only detected 2, and we've detected about 88 of these. The black hole mergers, the binary mergers, are much shorter in duration because they're high mass, so they evolve more quickly and they terminate at lower frequency. And so if you compare the time frequency maps, right, similar maximum frequency at which you can see something, but the duration is so much smaller. This is only a tenth of a second. So the duration of this event is the same as that, or that, or that, or that, maybe a bit shorter than the air compressor. There's almost no structure here. There's a little bit of chirping, right? You can see a bit of chirping, but this structure is close enough to, say, a blip glitch that there's a very high degree of overlap between them, or there's a very high likelihood that a blip glitch could give you a good overlap with your binary black hole template. So if you're only looking with a single detector, you basically can't see binary black holes. You won't. You can run the match filter search, but you'll be flooded by these guys. And your waveform morphology comparisons will fail you because there's not enough structure in here to be sure that it's not a blip. Whereas here, there's a lot of structure because it lasts for sort of 10 seconds or more. That's why if we go back just very quickly, this event was a binary neutron star merger event. If it had been a binary black hole event, it wouldn't have been confirmed as a detection. Right? There's no way you would have been able to tell it apart from the multitude of glitches in the data stream. So that's a bit of a shame. So this is what we can do with one detector. So if I go back over my 4 source classes, pulsars, they're easy. And that's because the binary neutron star lasts for, say, 10 seconds. Glitches don't. Well, the pulsar lasts forever, for a year. So it's relatively easy to do. You can, and we typically do this search with a single detector. You take your most sensitive detector, you filter the data for these signals, and you don't worry about glitches because they don't match the year duration and the modulations for pulsars. So pulsar's fine, single detector. Everything else is really severely hampered. For compact binaries, as we've seen, you can detect binary neutron star signals with one detector with difficulty and with poor sky localization. It's easier if you have some sort of external counterpart that tells you that thing is less likely to be a glitch. So for example, if you had a gamma ray burst, this is a artist's rendition of the binary neutron star merger with a jet for a gamma ray burst being launched. If you see a flash from a gamma ray burst at approximately the same time as your event in the data, then you're more confident, right? You can do a probabilistic association. It makes it more confident that the thing you're seeing is real and not a glitch. But again, this applies in principle to any other well-modeled transient that's complex, that has some complicated time-frequency structure, so that you can say with statistical significance that it's distinct from a glitch. But simple things like short-duration binary black hole signals, no. We can't do that with a single detector, realistically. Unmodeled bursts, again, theoretically possible if you had some sort of trigger, like if we had a supernova early warning system alert, right? A gravitational waves neutrino signal from a galactic supernova, right? Gives you a big neutrino pulse. We'd know within a few milliseconds the time at which the core bounce happened in that star. We could look in the gravitational wave data in some narrow window, a few seconds around, and hope to pull out something that you can compare to, say, catalogs of core collapse supernova waveforms. But it's very, very difficult. And in practice, this is extremely difficult to do anything. And stochastic backgrounds, you forget about it, because the entire procedure is to cross-correlate 2 data streams. If you don't have 2 data streams, you're out of business. Okay, so I hope I've made the case that it's really important you have more than one detector operating. So I'd like to talk for the remaining time, focus on what you can do with multiple detectors that you can't do with a single detector, or that you can do so much better, and the basic idea of how networks work. So these images here, I'm sure you're familiar with. These are the current operating detectors. So we've got LIGO Hanford and LIGO Livingston in the US. We've got the Virgo detector outside of Pisa. And of course, this is obviously an artist rendition cutaway view because it's under a mountain. But the Kagra Observatory that started operation a couple of years ago in Japan I will note actually as a highlight, the LIGO, Virgo, and Kagra collaborations have just recently published our first joint paper where we're using data from the multiple observatories collectively, including Kagra, in an analysis. Their sensitivity is very low at the moment, so we don't have very strong astrophysical limits, but it's a nice milestone in the global network to have these first results come out. Okay, this is another image of the global network. It's my best effort to try to show geometrically where everything is, because this is actually really, really important to how the network functions. The most important thing you can do after deciding to build a detector is to decide where to put it. So this is, so we've got LIGO Hanford and LIGO Livingston in the US, and we've got Virgo. It's just around the edge of the Earth there. You can see the boot of Italy, placed it approximately. Kagra detector around the other side in Japan. And then under construction, as we've heard, LIGO India, which is, again, through the Earth in India. For comparison, so by, say, 2030-ish, hopefully all of these detectors will be operating with good sensitivity. And it's these baselines that form the basis of how we can do multi-messenger astronomy with the gravitational waves. In particular, okay, pop quiz. What's the diameter of the Earth? Yes. Yes, but what is it in seconds? Right. Anyone? It's not a number you're used to using, right? It's 21 millisecond radius. Okay? So from the center of the Earth to the surface is 21 milliseconds, so it's 42 milliseconds across. So I just point this out. It's another way in which gravitational wave astronomy and traditional astronomy, you just have different modes of thinking. When I look at the Earth, I think it's about 20 milliseconds across. When I look at the network and these distances, I think about them in milliseconds rather than in kilometers, because milliseconds is something I can relate to the gravitational wave measurements. Let's see how that works. So let me just remind you again, we had this problem, the glitches, right, that are absolutely hammering your single detector. So this is, again, for Hanford, but Livingston, Virgo, they all look like this, something like this. You've got glitches on the order of 1 per minute that are large enough to swamp any of your search tools. So how do we handle that? So this is the first case, and I would argue possibly the most important thing that multiple detectors gives us. It's suppressing the background noise. It gives us a drastic reduction in these transient searches that otherwise are caught by glitches. So let's just run through the numbers. Let's just assume all the detectors glitch at the same rate, yeah? So once per minute. I'll take Hanford. I've just got the Hanford detector operating. It sees about a glitch every 60 seconds. That's too much, right? It swamps my search. So if I go back quickly, the LIGO detectors, this distance is 10 milliseconds light travel time. So if it's a gravitational wave hitting Hanford, there should be, within plus or minus 10 milliseconds, the same wave hitting Livingston. So that's what we call our coincidence window, plus or minus 10 milliseconds. Now, it's possible that I could have a glitch at Hanford and an independent noise glitch at Livingston at the same time to within plus or minus 10 milliseconds. That would be a false alarm. That would be bad. But it's much less likely to have two glitches within plus or minus 10 milliseconds than to have one glitch on its own. So you can do the math, right? If I added a second detector, so I've got the rate of, assuming again the rate of glitches in Hanford and Livingston are both, say, 1 per minute, and then this t is the 10 millisecond coincidence window. So the rate at which I get coincident events is the rate in each detector multiplied by that timing window, two times the window, because it's plus or minus 10 milliseconds. So you just work it out. It's one event per 2 days. So that's basically for free. If you require in your analysis that your search, your matched filter or burst search, pings off at the same time to within 10 milliseconds in each detector, then suddenly your coincident glitch rate is almost manageable. One per 2 days. Still not enough, but much better. Now throw in the Virgo detector. The Virgo detector is about 27 milliseconds away from Hanford. That's the largest baseline in the network. So if I do this, I just daisy chain. I add more detectors in. I add in another 1 per 60 seconds, multiplied by roughly 60 milliseconds. Every one of these I factor in. It works out to be about a factor of 1,000 reduction. I'm now down to less than one false alarm per year. Less than once per year, LIGO and Virgo and LIGO Livingston, LIGO Hanford, and Virgo would all ping off with a glitch within the required few millisecond coincidence times. So, I mean, it's really simple math. That's it, right? But it's absolutely vital. We have not yet found any way to suppress the individual detector glitch backgrounds enough compared to the simple coincidence requirements. right? So this really is key to how all of the transient detection searches work, and it really is as simple as that. So in practice, we don't normally require seeing an event in all three detectors. I'll explain why in a moment. It's because they look at different parts of the sky. So typically, a given search code typically only requires seeing something in two detectors at the same time. The details vary with each individual search code. And what we rely on instead is further reduction in the background. So for example, as I mentioned, this idea of a chi-squared match, if you've got a template, like for a BNS system, for example, you require that the signal you see in the data has a good chi-squared match to your template. That can get rid of a lot of the glitches that don't have the right morphology. If you're doing an unmodeled burst search where you don't have a template, you cross-correlate the two detector data streams, and you look for a strong correlation. And again, that just removes glitches that are of different types in the different detectors. If you're unlucky to have two blip glitches go off at the same time in Hanford and Livingston, you're sunk. You're still sunk, but that's what we can do so far. Okay, so I said, one last point. The other thing that's absolutely vital is we need at least two detectors to make the stochastic search as possible at all, right? Because they're cross-correlation based. Without that, you can't do a stochastic search. Okay, so I wanted to go back at this point here, how we actually require coincidence in networks and why two detectors. So this is a plot that shows 4 of the detectors and their sky coverage. So this is the antenna response plots we've seen before. So this is the Hanford one. I've suppressed Livingston because it's almost the same as Hanford here. I'm going to switch from the top left Hanford to Livingston. You can see that they're pretty similar, and that's because the detectors are only, I think, 23 degrees apart on the Earth. They're relatively close together on the Earth's surface. So they have similar antenna responses. Okay, and what we see, very important, something that's very important in practice, is that the detectors, while they are roughly all sky monitors, they observe large portions of the sky, the different detectors in the network point in different directions. So Hanford and Livingston, as Barry explained, were designed to point to be as well aligned as possible. So they look at almost the same point on the sky as allowed by their positions, and as we'll see in a moment, they see almost exactly the same gravitational wave polarization. But the other detectors, right there, they are wherever they were built, and so they're pointing basically straight up and straight down for them. And a key thing is that, historically, it's been the LIGO detectors and the Virgo detector that have been operating with high sensitivity for the last few years. And so those are the ones that are making the detections, right? LIGO India is not operating in Congress, just come on and started to get some sensitivity. And so if you stare at these plots for a minute, something becomes evident really, really quickly. Virgo is pointing here, and Livingston and Hanford are pointing there. So LIGO and Virgo look at basically orthogonal patches of the sky. Let's compare that again. So this is, again, that's the direction of the sky that's directly above the Virgo detector, and you've got the antipodal point, which happens to be in this particular projection, smeared along the bottom there. But that Virgo, the Virgo zenith of maximum sensitivity, almost exactly coincides with the null of the Hanford-Livingston network, right? So where Virgo sees the best, LIGO tends to not see very much at all. And where LIGO likes to detect things, above and below North America, Virgo has a null. And so it's actually, if you look in the papers, it's a common occurrence. The things we detect are relatively strong in LIGO and pretty weak in Virgo, and it's just because of this, it's the geometry of where the detectors were put. That's not something you can easily change, but it's something that's really important when you're doing analysis. So for example, in the unmodeled burst searches that I mentioned, I think Eric will talk a bit more about them, you're regularly correlating between pairs of detectors. The problem with doing those sorts of searches with the LIGO Virgo network is, again, that the signal in Virgo tends to be less correlated because Virgo has best response in a different sky direction. If it's coming from a direction where LIGO sees it, Virgo will have a low sensitivity and low correlations. So this is a technical challenge, but it's a standard one, particularly in the burst searches that rely on these networks to fold in Virgo and get good sensitivity from the results. On the positive side, as these other detectors come online in the coming years and become more sensitive, their different orientations mean we will be covering the entire sky. Right? When all detectors are operating, there's nowhere that a signal can come from where we don't have some hope of seeing it. Right? It'll register in some of the detectors. Right, so that's Hanford and Livingston. I wanted to briefly comment on the overlap. I'm sorry, I don't have a good graphic for this, but if you have a detector, right, it's got an X and a Y arm, and I'm just going to call those. So this is my interferometer, right? This is technically gifted as I am at drawing interferometers, right? Your X arm and your Y, they're not even the same length. It's terrible. So that's your X arm and that's your Y arm. So they have a pointing direction, X hat and Y hat, the direction the two arms point in. We define this detector matrix. It's just this geometrical combination, but it encodes which way your arms are pointing, yeah, for your detectors. So you can look up where each detector is and where their arms are pointing, and then you can do this overlap. Basically, you take detector I, detector J, you multiply the matrices together and take the trace. And it gives you a number between plus and minus 1 that's a measure of how closely aligned the arms are for measuring the same or different polarizations. So it's a simple measure. And then this is the matrix of those numbers. So obviously it's symmetric, so I left these ones blank. So each detector is, of course, perfectly aligned with itself. The Livingston detector is almost perfectly aligned with the Hanford detector. As Barry said, that was by choice. They tried to get the arms as parallel as possible so they see the same gravitational wave polarization. So you'll have, as near as possible, exactly the same signal in Hanford and Livingston, and therefore the most confidence that you've seen a real event. The minus sign often catches people, particularly students. It's because the detectors aren't aligned like this, they're aligned like that. There's actually a 90-degree rotation of one to the other, which gives you the minus sign. That's not important, obviously, except for when you're coding things up, you have to make sure you get the signs right. And then this, the Virgo detector, in addition to looking at a different portion of the sky, right? If you do the overlap, in particular with Hanford, it's basically zero. So the Hanford and the Virgo detectors are essentially completely orthogonal in what they see. And again, when it comes time to actually doing sort of a coherent network analysis, particularly in the unmodeled burst case where you rely on correlating between detectors, that makes it technically challenging. There is some better overlap between Virgo and Livingston, but generally it's challenging to fold the Virgo data into these unmodeled searches. And then the near future detectors, Kagra and LIGO India. I mean, interestingly, Kagra has sort of moderate to reasonable overlap with all of the existing detectors, and then LIGO India in particular is particularly well aligned with Livingston, to a lesser extent with Hanford, according to the current orientation that I've coded up. So I just wanted to point out, really, it's these two numbers. I'm supposed to highlight them. There we go. Really just wanted to highlight, again, this is a very important practical consideration. Hanford and Livingston basically see the same gravitational wave. Hanford and Virgo see sort of orthogonal portions of the gravitational wave universe. Right. The next topic, things you get from a network. In addition to covering the sky, you cover in time. These detectors aren't operating all the time. They're really complicated instruments. Typical uptime, if you look at recent papers, typically around 75%, sometimes a little bit lower. So that is during an official observing run, what fraction of the time the instrument is in science mode collecting quality data. The other 25% of the time it's not in science mode and not collecting necessarily good quality data. So if you just take 3 detectors, Hanford, Livingston, and Virgo, you look at the numbers from the first half of the latest science run, 03A as it's called. This is the pie chart of how much time out of those 6 months any given combination of detectors is operating. So roughly speaking, you take 70% or 75%, you take the cube of that, right? You get down to around 40%. Hanford, Livingston, and Virgo, all 3 of them are operating close to half the time. That's great, right? So you've got all 3 detectors observing the sky. Hanford, Livingston alone, without Virgo being on, that's another 14%, or Livingston, Virgo without Hanford, another 14%. There's a small amount of time when Livingston was not on, but Hanford and Virgo were. And then finally, there's 21% of the time, which in sort of my world is sort of waste time, downtime. 0 or 1 detectors were operating. And again, for my kind of work, 1 detector is not very useful. And that's a pretty reasonable chunk of time. If the next core collapse supernova in our galaxy goes off during the next science run, right, that's a 1 per 100-year event. There's roughly a 1 in 5 chance that we won't be on, right? And that's rather terrifying. So if we have 1 detector on, we'll do what we can to salvage the data, but it is terrifying that these rare events we could miss. So you want to have as many detectors operating just to maximize the lifetime. So for example, if Virgo wasn't operating during that run, this 8% and that 14% would have been lost. It would have fallen into this category. And we go from 21% to 43%, something like that, downtime. So it's really important to have multiple detectors operating for that redundancy. Right, so the next topic on what you can do with multiple detectors, why you want multiple detectors, is to me the least interesting and the least useful, but it's one of the most commonly quoted. If you have more detectors observing an event, you can build up the SNR, you get better measurements of the properties. That's true, but it's also not true. So let's go back to this plot. This is the plot of the LIGO Virgo noise spectrum at the time of gravitational wave 170814. This was the first event that was detected by Virgo, where you can explicitly see a peak in the SNR, and it's clear that there's an event in the Virgo data. You can see the Virgo noise spectrum is a bit higher than the LIGO detectors at the time, but as we'll see, so the signal was detectable, but at a lower signal-to-noise ratio because of this higher noise. So what I want to point out is that when you do a full coherent or Bayesian analysis of the data, if you've got all three detectors operating, yes, you can combine the data streams and do a coherent combination. But when you work out the signal-to-noise ratio, signal-to-noise ratios don't add up. They add in quadrature. And so here's the data. This is the Hanford signal-to-noise as a function of time in Hanford, Livingston, and Virgo. You see the filtered data down here. You can see the waveform, the best fit waveform in each case. These are your time frequency maps. The key thing are these SNRs. So it was seen most clearly in Livingston, peak SNR of 13.7. So that's clearly an event. 7.3 in Hanford. Not as strong, but quite clear. So based on these two numbers, you're sure there's a gravitational wave. There is a 4.4 SNR in Virgo. It may not look as impressive, but I mean, this is basically a factor of 2 jump from the background to that value. So it is statistically significant. There is a signal there in the Virgo. If you add the Virgo data in, you can hope for better performance. Well, but the SNR is adding quadrature. So the top line here is what you get if you just add in quadrature the SNRs including Virgo. If Virgo hadn't been operating, you would have had the denominator. The ratio of those is 1.04, right? Because of the quadrature adding, if you have a less sensitive detector added into the network, and that's common, right? When the new detector comes on, it's usually less sensitive than the older ones. Virgo isn't a new detector, but the project started about 2 years after LIGO, so it's it's 2 years behind, in project. Or LIGO's had 2 years advantage to get ahead. So when you add in a less sensitive detector, basically the extra SNR isn't worth anything. That 4% is smaller than any of your statistical uncertainties on any of the measurements. So it doesn't really help you do, in principle, you get marginally more detections. You can see 4% further, or you can get 4% better constraints on some masses or something. Doesn't really make a difference, right? And in fact, in transient searches for bursts, it's quite common, including for CPCs, it's quite common in LIGO Virgo to just use the LIGO and Virgo, the Hanford and Livingston data streams initially to do detections, and to not bother with the Virgo data stream until you've got an event and then you want to do parameter estimation. Now that's actually where the Virgo really comes in as a beautiful help. So adding in that 4.4 SNR doesn't help much for doing things like masses, but it can have a dramatic effect on what we call the extrinsic parameters, in particular the sky location. So this is the last bit I wanted to focus on for my allotted time. This image is what we call the sky map and the distance posterior for this same event, the same gravitational wave. So as I'll explain, if you just had Hanford and Livingston, and we did do this analysis, using just the Hanford and Livingston data, the sky localization error box is this sort of yellow banana. It's quite a large area. You add in the Virgo data, and we get this much smaller ellipses. There are actually two here. The green one was done in what we call low latency. It's a fast analysis, not the full Bayesian. And then this sort of weird purplish multi-lobe structure is from the later full Bayesian analysis. The key part is that pick either of these ellipses or both. This area is dramatically smaller than the large banana. And the reason is because that SNR in Virgo, as we'll see, it's a small SNR, but it tells you the time that the signal arrived in Virgo, and so you can triangulate the sky location. So that's really important for getting, if you want to tell an astronomer to point a telescope, you can't point them at this banana. That smaller ellipse is searchable with large field of view instruments. So that's a dramatic reduction, and that's where having extra detectors, even if they aren't very sensitive, is incredibly valuable and gives you a lot of science. I'll just point out the distance posterior here. The green and purple ones are noticeably narrower than the LIGO-only distance posterior. So that helps for things like Hubble constant measurements if it's a binary neutron star case, for example. And again, the reason it's narrower is because if you don't know where the signal is in this large banana, the LIGO antenna responses change quite a bit when you go from this end of the sky all the way over to that end of the sky. And so for the higher antenna responses, the signal must be closer. For the lower antenna responses, the signal must be farther. It's a larger uncertainty. If you can constrain the region in direction, you can also constrain the distance much better. So that's all really useful. So source localization is the last topic I want to cover. But it's really fundamentally important for multi-messenger astronomy. So Marika Branchesi will be talking about this, I think, tomorrow, first lecture, on gravitational wave, no, Thursday, sorry, multi-messenger astronomy with electromagnetic telescopes and gravitational waves. And so I just want to lay the basics of how it works. So the basic idea is triangulation. So I mentioned this time of arrival of that gravitational wave signal in Virgo. Even though it was low SNR, you could see the time at which it arrived, and that's key. So this diagram is again from this Observing Scenarios paper. It's actually copied from an earlier paper here. And so this schematic, this is supposed to be the celestial sphere. And the dots indicate the locations of our three current operating detectors, Hanford, Livingston, Virgo. We have a gravitational wave coming from this point S on the sphere. Yeah? So the gravitational wave, basically, it's coming from upper right. So if you kind of squint, you can imagine that a plane wave coming in from this direction, right? The wave fronts are sort of going this way, so they're going to hit Virgo first, and then maybe hit Hanford sometime later, and then a very short time later they'll hit Livingston. So you get three different arrival times at the three different sites, which are determined by where the detectors are and the direction to the source. Each of those times, so for each pair of detectors, I can then do a time of arrival difference. So for example, I measure the time delay between Hanford and Livingston. So it just comes out of the data. What was the time of arrival difference? This red ring on the sky indicates all positions on the sky from which the signal could have come and would give you that time delay difference. So basically, it's just a cone. So this red axis is just parallel to the Hanford-Livingston baseline, and this ring is concentric around that axis. So any of these points on the sky are consistent with the measured time delay between Hanford and Livingston. And then you repeat for the other three pairs of detectors. So I've got Livingston, Virgo, this blue axis, with some time delay along that axis constrains the signal to be on this blue curve, and then for Hanford, Virgo, I've got the green time delay. Where the three rings intersect is the place where the signal came from. It's one of only 2 points on the sky that are consistent with the time delays in all three detectors. I say one of only two. There's a mirror symmetry in this plane. So if I reflect through the plane, there's an antipodal point that also gives you exactly the same time delays. Typically, you can tell the difference between these two because the antenna responses will be different for that point and that point. And so you'll be able to say, oh yeah, well the amplitude in each detector is consistent with the antenna responses there, but not consistent with the antenna responses there. So usually you can tell which point is the right one. There is a catch, of course. If you look at the details, you should read the paper by Fairhurst, 2010, Source Localization. It's the classic reference for all of this. He shows that, if you want to go into a little more detail, these rings, I mean, I've drawn them as very thin rings, but in fact, they have some thickness, and you can measure the thickness, you can estimate the thickness. It works out to order a degree, depending on the bandwidth of the signal, and this is the baseline, the distance between your detectors, divided by speed of light to make it a time. And the signal-to-noise ratio, roughly speaking, the signal-to-noise ratio in the pair of detectors. So I put in the numbers sort of at detection threshold, scaled to the Hanford-Livingston light travel time, and 100 hertz is a reasonable value for signals. But what it means is that, remember, the Hanford and Livingston are 10 milliseconds apart. Virgo's about 30 milliseconds away from the others. So actually, these rings have varying thicknesses. So this is a really crude cartoon version, but I've just rescaled the rings. So in practice, the Hanford-Livingston ring will be much thicker than the rings that contain the Virgo time delays. And so you don't get a single point, right? You get at best an extended region, the ideal case. If one of the detectors isn't operating or not operating well, so for example, if Virgo's not operating, then we fall back to just having this great big ring, big fat ring around the sky, which is the only constraint we can place. And then generally that ring you further modulate by the antenna responses. So some parts of the ring your detectors won't have very good antenna sensitivity to, so they're less likely to be the true source location. And so what happens is that in a lot of cases, particularly when you see a signal clearly in only two detectors, the sky map tends to be a portion of one of these time delay rings. That's determined by which detectors saw it. So this is an image that shows all of the sky localization maps from all of the signals detected in the first two science runs. It was just enough that you sort of fit on one plot without being crazy. And what you see, so for most of this time it was just the two LIGO detectors operating, so most of the detected signals are these long banana shapes. They're just sections of arcs of constant time delay between Hanford and Livingston. And then there are a few cases where Virgo was on, Virgo was sensitive. So we see down here, for example, the 1708-14, this three detector event, the first one detected by Virgo. We've got this much more constrained space. And the other famous one, the binary neutron star merger, not actually seen detectably in the Virgo data, but Virgo was operating, and the small SNR allowed us to constrain the position, even though there wasn't a clear signal in the Virgo data, constrained to this very small region. So that's the importance of having a third detector, right? If you have two detectors, then these are the maps you're looking at. If you have a third detector, then these are the more typical maps that you're looking at for pointing telescopes. So there is a complication. Sorry, I just wanted to point out, some of these maps have this weird double lobe structure. So I just wanted to briefly comment on what's going on there. If you're at the right sky location, yeah, if you happen to guess or you know where the signal came from, then in the analysis, of course, you want to shift the data series from your two detectors or three detectors to line up the signal in each detector so you can coherently add them. So say I've got Hanford and Virgo operating. This is my binary in spiral. If I know the right sky location, I shift them in time so that the peaks line up and the troughs line up, and then I coherently combine the data, and I get a nice buildup of my signal. Right? I'll get a high likelihood or a high Bayesian posterior. But I don't know the sky position a priori. And so typically what I do is I work on a grid of possible sky locations and do the time shifting and the coherent combinations for each one. What happens if I'm at a nearby sky location that's off by approximately one cycle of the signal? I say approximately. You'll forgive me. It doesn't work exactly. But suppose what I've done here is I've taken the Virgo data and I've shifted it so that this peak, instead of lining up with its matching peak in Hanford, is one peak over. Now, obviously, it's not a perfect alignment of the signal, right? I've got this peak lined up with that peak. That peak is almost aligned with that peak. That peak's aligned with that peak. It starts to go to phase. Like, by the end, it's a mess, right? You're completely out of phase. But there's a long stretch of several cycles there where you're more or less in phase at the new sky location, at the incorrect sky location. The signals are lined up in phase. And so if you don't know which is the right one, so you do your coherent analysis, this sky position will give you a pretty reasonable coherent buildup, a pretty reasonable coherent SNR. You're most vulnerable to this if the signal is only in band for a couple of cycles, right? If you can see all of the cycles quite clearly, then you don't have this problem. So obviously, at this frequency, I can shift by one period, whatever the current frequency is there. But obviously, it doesn't keep in phase at these higher frequencies. So the broad bandwidth signals, you don't have this problem. That's why binary neutron stars, for example, they're much more easy to localize. But a narrow band signal, there is the potential for this issue. And so here's another example. This is 1908-14. So this was a rather high mass system. I believe it was, not terribly high mass. I think it was 23 solar masses plus 2.6. But this is one of the sky maps that shows this effect. So this is the Hanford-Livingston banana, right, without the Virgo data. And here you've got kind of an echo of the banana. Best guess is that the true source location is in this big banana. It might be in that small banana. It's probably in one of those two. But what's happening is that one of these bananas is when the time delay between Hanford and Livingston is out of phase by about one cycle of the peak power of the peak frequency of the signal. And so your coherent analysis can't be sure which one is the right alignment. Virgo still really helps here. You see, so the Virgo, you can imagine the Virgo time delay line sort of cutting through in this direction, and it cuts you down to two small portions of these bananas. So again, a demonstration of the power of having the Virgo detector, even if it's not as sensitive, may not help you with things like mass estimation, but it's really dramatic and really essential for multi-messenger astronomy. You need to have multiple detectors operating to do this. It makes a qualitative difference to your multi-messenger astronomy. Okay, this is my last contentful slide. A first look ahead. So this is the Hanford. The plots are taken from this observing scenarios paper from LIGO. It's actually from version 1, which I was one of the main authors of, and we're now on about version 15, and it's a completely different paper. I like the original version. That's just, me officially. But I like it because it has this plot. So these are plots that were made by, following the work of Fairhurst on time delay triangulation. They really show how you need a network to do multi-messenger astronomy sensibly. So this is the Hanford-Livingston-Virgo network, the top left plot. So what's happened is, for each point on the sky, you imagine you've got a binary at some fixed SNR coming in, or at some fixed distance rather, and you work out the expected average localization area. It's basically by the time delays, the size of the error boxes from these bananas. If you have just the three Hanford-Livingston-Virgo detectors, what you see is you see that your receptivity is not constant, or your sky localization isn't constant over the sky. And what happens is that if you have best sensitivity for a signal coming directly over the plane of the three detectors, so that gives you the smallest error boxes. So signals sort of coming over the North Atlantic or the antipodal point give you the best localization, the best timing constraints. It's just a function of the geometry. For detectors that come in the plane, that's this band. Yeah? Signals that come in the plane of the detectors are represented by this band. So a binary signal from any one of these directions would be coming in the plane of the detectors, and your triangulation is worst there, and you get the worst sky localizations. It's just an unfortunate fact, in particular, that a lot of our good observing sites are here, right, in South America, in Chile, and so it's just a coincidence of the geometry. Most telescopes see best straight up, right, where they're looking through the least sky. So if you had a source that was ideally located over one of these large telescopes in the southern hemisphere, it happens that our error boxes would be the largest for those. It's just bad luck, right? It's just a function of geometry. The way you cure that is you add in extra detectors. So this is, if we skip down here, this is if you add a detector in LIGO in India. So that's basically the other side of the world, very far away from the LIGO Virgo network. You've got a long baseline and a detector in a different location. It gives you another set of timing delays that allow you to severely constrain the sky localization. So these areas are more typically something like 5 square degrees, and you get a much more uniform coverage of the sky. So this is the last plot I wanted to show, but it really stresses to me the importance of having a network of detectors spaced as far around the globe as possible for doing multi-messenger astronomy. Because this you can give to an astronomer. These are much, much more difficult. It's much easier to follow these events. Okay, so I'll stop there. I think I've come to almost exactly 75 minutes, which is my allotted time. I apologize for that. I just wanted to point out, for this first lecture, we wanted to cover the basic ideas of gravitational wave emission and the quadrupole approximation, and how that then maps onto the classes of things we could hope to detect. I've just very briefly outlined those main source types. As I said, Eric will cover them in more detail in his lecture, but the main reason was then to look at how detector networks work, and I hope I've given you some idea of how, in practice, we can do detection confidence, noise suppression, sky localization, some of those other key issues in gravitational wave searches. Right, so thank you. I'm happy to take questions. Yes?
Thank you very much for the insightful talk. I have a rather pessimistic question. So let's say we have the scenario where we get a detection by 2 detectors. So we have a ring, and then we have a glitch on a 3rd detector. I think supernova binaries get similar duration to blimps. Is it possible in that case that we get a false localization, and how can this be overcome?
Yeah, so the question is, if we have a glitch that overlaps our signal, can that throw off our localization, especially if if it dominates the signal in one of the detectors? That's a good question. That has, in practice, happened. For the binary neutron star, the first one, 170817, the multi-messenger detection, there was a very loud blip glitch that occurred, I think, about 0.7 seconds before the merger, and it just cleanly cut right through the signal. And so in that case, because the blip glitch is a fairly simple morphology, what was done was the analysts were able to actually fit the shape of the glitch, knowing other examples of that type, fit it and subtract it out. And it was demonstrated that removal procedure had sort of minimal biasing on the gravitational wave reconstruction, etc. There are studies going on of what happens if you have other glitch types at different distances away from the merger time, etc. There is some potential for bias. What we would have to do is, I think what we did for that first binary neutron star event is try to fit out the glitch. At the moment, it's sort of manual. I think the efforts are underway to automate that, to fit out the glitch and remove it coherently. But that requires having other examples of that glitch type. So that's okay, because you're most likely to see a glitch that you've already seen before because they're frequent. You're less likely to see a rare glitch. But that would be the approach, yeah.
Thank you.
Okay. Hello. An excellent talk. Thank you very much. So I have 2 questions. First one is about the matching of the signals from different detectors that you showed before with the event 1908-14. If you could go 2 slides before that.
That sort of schematic?
Yes,
yeah.
I have a question. Why do we not choose to match the ring down or something like we know the particular formula that is correct? Why do it before?
Right. Yeah. So I'll stress. So the idea here, obviously, this is just sort of hand wavy, but the idea is this is the raw signal without accounting for the noise spectrum of the detector. So imagine a case where these particular frequencies are such that this portion of the signal, the merger ring down, is at high enough frequency that we can't really measure it. It's under the noise floor. In that case, so you can imagine the detector only has good sensitivity over some finite band. So suppose that finite band is basically this portion of the signal, and we don't really see that portion or maybe that portion so well. That's a scenario where you could get into this confusion of the offset by one problem. But it really only happens in special cases. I'm saying for binaries it only happens in special cases. The image, I think it was this. Right, yeah. So if you look at this example, all of the results from 01 and 02, right, there's that one case. I don't think there are any other examples from the first two science runs where you see that extra structure. But I was just pointing out that it can happen. It's likely. My bet would be that it's likely to be a more serious problem for unmodeled burst sources where we don't know what the waveform is outside of, and we're just correlating between pairs of detectors. But we haven't detected any unmodeled sources yet. Yeah. So, but fundamentally, the trick is this. As you can, I guess it's obvious graphically. If I go to the next one. The characteristic of this signal is that it has a broad band. It has multiple frequencies from low to high. And you can't time shift in a way that all of the frequencies match up, right? You can match over some band, but you can't match these frequencies. So that's why having a broad bandwidth is essential to getting the localization correct.
Yeah. Okay, thank you. And the second question would be about the physicality of the potential physicality of glitches. Could there be some events that we consider to be glitches because we don't have models, but the profiles that we already have could be something, or even if we take the signal from different directions and inclinations and everything, they would have the same signals, a different profile that could have a meaningful.
So, sorry, just to make sure I understand, are you asking, could we mistake a real signal for a glitch because we don't understand the morphology or the
Yes.
detectors have different? That's a good question. I haven't really thought about that before. I'll tell you, it doesn't keep me up at night. The detectors have broadly similar shaped noise spectra. So like Virgo may be higher, the LIGO detector may be lower, but the general shape is the same, which means that you're seeing basically the same band in each detector. It's just a matter of different heights of SNR. So I'm not terribly worried about dismissing an event because it appears different in the different detectors. It's much more likely that we're not confident in accepting it as a real event because it's too weak or there's a glitch contaminating the signal, something like that. I'm much more worried about dismissing it because, not because of different morphologies in the different detectors, but rather just the bad noise in the detectors or bad antenna responses. The only example I can think of would be a core collapse supernova. Let me see, I did have a backup slide with an image of a core collapse supernova simulation somewhere there. Yeah, obviously this was a draft slide, right? I haven't corrected the colors here. This is an image from a core collapse supernova simulation. And what we see here is, it's the boiling convective motion in the inner core at some point shortly after the core bounce. And so the scale here is, I think it's minus 1,000 to plus 500 kilometers, right? It's of order of 1,000 kilometers. So it's the sort of maximum size you expect to be able to measure. The motion on these length scales is kind of random. Like this bit here is not correlated in its motion with this bit here or that bit there. So for a signal like this, if you look at the time series gravitational wave that comes out, it tends to look like noise. It looks like random noise with some particular frequency range and duration. What we call noise burst. We can detect those even though it looks like noise, because it's the same noise. If you have, say, Hanford and Livingston, which are well aligned, they'll see that same noisy signal, and so a cross correlation will still pick it out. But if it's Hanford and Virgo, as we've seen, those see orthogonal polarizations. And if I try to cross correlate the Hanford data with the Virgo data for a random signal like that, it's quite possible that the correlation is not very strong, because I'm detecting sort of the plus polarization from the random motion in Hanford and so the cross polarization from the random motion in Virgo. It's not clear how well we could measure that sort of case. So that's the one case I would be worried about of perhaps falsely dismissing or not being able to claim a detection because of dissimilarity in the detectors, dissimilar signals in the different detectors. I think the only way is to have random motion involved to give you a random signal.
Thank you. Thank you.
You're welcome.
Thank you for your talk at first. I would like to ask a question concerning mostly the sources.
Yes.
Is it possible to detect collision of black holes that are head-on, and what kind of signals do we expect to have, and if it is detectable from the current detectors?
Yeah, so those are detectable. I believe we don't. I'm pretty sure we don't do any dedicated searches for that specific type. But I mean, I think the gravitational wave emission from a head-on black hole collision was basically one of the first things that was solved, right, in the early days. And Alessandra actually showed the waveform for the case of a point mass falling into a black hole in a head-on collision, right? So it's a fairly simple signal, a few oscillations. It would be the unmodeled burst searches that we do that basically just correlate pairs of detectors over short time periods would have no problem picking up that kind of signal. The difficult bit would be, okay, the burst search has reported a signal. It's something that just oscillates a few times and cuts off. What was that? And so I would say the biggest unsolved problem in that area of the work is actually when we get a burst signal, if there's no supernova or gamma ray burst to give us a clue, if it's just something that wiggles a few times in the data, it's clearly correlated between all the detectors, well-defined position, etc. But we have no idea what the morphology, what made that signal. That would be to me actually a very big unsolved problem in the field. But yeah, radial head-on collision I think would show up quite clearly in our current searches.
And second question, about galaxy collisions, what could we infer, or could we detect them right now, or mostly with the supermassive black holes and with dark matter content?
So for the galactic collisions, we have to go to, I think Stefano Vitale is going to give a talk. I think it's the first talk tomorrow morning on space-based detectors. Supermassive black hole binaries, it's the same gravitational wave signal, but scaled up by 1 million to 1 billion. And so the time scales are much longer, the frequencies are much lower, and so we need the space-based detector. I will have some comments on looking for dark matter with gravitational wave detectors, the ground-based ones in my Friday talk. It's a topic of particular interest to me. So if you don't mind, I'll save that till then when I can show you some ideas in a little more detail.
Thank you very much.
You're welcome. Wildly over time.
Okay. One last question.
I'm happy to talk over lunch as well, right? Okay. If you want to. Okay.
During lunch.
Sure. Yeah.
So you showed an example where Virgo had a very low signal to noise and that helped localize a particular event. Could you use a non-detection by an operating telescope to also do that? Let's say, okay, if it's here, we should see it, and we don't.
Yes. Do I have a plot of 170817? Okay. I don't have a plot handy, but for the first binary neutron star detection, 170817, it was seen clearly in the LIGO detectors. Virgo was on, operating in good condition, but there was basically zero SNR. There's no detectable signal. And so what that meant is when you do the full Bayesian analysis, it must have come from one of the points on the sky where Virgo had basically zero antenna response. So on those plots, we've got the 4 spots, right? On any of these antenna response plots here. Yeah, so what it meant, so this is Virgo, so what it meant is the signal had to come either that point, or that point. And then that one of those overlapped the LIGO banana, and that was it. And the counterpart was found 11 hours later by EM telescopes. So yeah, so a zero SNR is still informative if the detector was operating, and if you do a full Bayesian analysis. All right. Thank you very much.